Okay, so in this lecture today we will see about descriptive statistics and statistical inference, and in particular two tools that are coming from statistical inference that are hypothesis testing and power analysis. So let's start with the descriptive statistics. So we will use examples that are very easy to understand, not necessarily related to animals, but I have chosen them because they are easier to follow. Okay, so let's say that you are an engineer, that you work for a pharmaceutical company, and you are in charge of the manufacturing machine that has to put 250 milligrams of a given compound in all tablets. And the manufacturing process is not perfect, and you have small deviations. In particular, we have to make it technical, so it is a standard deviation of 1 milligram, and we will assume that this manufacturing process is Gaussian. So you are in charge of this machine, and if it is badly calibrated, you have to stop it, recalibrate it, and put it into operation again. So every week you take 20 tablets, and this week we have taken these 20, and these are the amount of the compound that are in each one of the tablets. I have sorted them by number, but when you collect them, they come out of order. Okay, so is it possible that the machine is malfunctioning? Should we stop the machine for recalibration? So looking at these numbers, should we stop it or not? It's hard to say. So descriptive statistics takes all these numbers and tries to construct a summary. So we can use different summaries. So for instance, we can make a histogram. So in this histogram, we count how many tablets we have seen between 248 and 248.5 milligrams. Zero this time. Between 248.5 and 249 we have seen 3, and so on. So it seems from the graph that the 250 seems to be a little bit on the left. So, but maybe we have been unlucky with these tablets, and the machine is good. Okay, so other summaries that we can construct, we can take what is the minimum, the maximum. So this is the minimum number, this is the maximum number. Altogether they make the range. Then we can compute the mean or the average of the amount of compound in all tablets. So in this particular case it is 250.66. So there is a deviation from the target composition of 0.66 milligrams. And we can also compute the standard deviation, we can compute the mode, the median, the sample variance, we can compute many things. We have to distinguish between the sample parameters and the population parameters. So the population parameters are the mean, the standard deviation, the parameters from all tablets manufactured by that machine, that we presume that they have these values, 250 and 1 milligram, the mean and the standard deviation. The sample parameters are the ones that we have observed particularly in this particular sample. So we have collected 20 tablets and in these particular 20 tablets, the sample mean was not exactly 250, but a little bit more. And the standard deviation was not exactly 1, but a little bit more. So this distinction between sample parameters and population parameters is very important. Okay, so these summaries, for the moment, they don't allow us to decide whether the machine is working correctly or not. So let us see if we can borrow another tool from statistics to take this decision. And this tool is hypothesis testing. So it reminds me of a saying of Sam Ewing, that was a baseball player in the US. An expert is someone called in the last minute to share the blame. So the hypothesis testing is that expert. So you want to rely your decision onto some quantitative expert that takes the responsibility of deciding whether the machine should be stopped or not. So this expert, you have to define for the expert what you want to prove. So we want to prove that the machine is malfunctioning. So that is what we want to detect if it is the case. So the alternative hypothesis is that the machine is malfunctioning. So the mean of the population mean of the tablets is different from 250. The null hypothesis, it is the opposite. So the mean is different from 250. The opposite is that it is equal to 250. We have to make here a point. We can reject the null hypothesis and then we accept the alternative hypothesis, but we can never accept the null. We will come back to this idea later in the next part of the session. Okay, so we can have 4 possibilities, and 2 of them we would be very happy with them. So let's say that the machine is malfunctioning, so the null hypothesis is false, and we decide to reject the null hypothesis. So the machine is malfunctioning and we correctly identify that, and then we would be right. We would be very happy to do that. The other possibility is that the machine is correctly working and we don't reject the null hypothesis, so we don't stop it for nothing. But there could be 2 errors. One is called false positive, the other one is false negative. So false positive is positive because you have rejected the null hypothesis, but it was false. So rejection of the null hypothesis here means that we think that the machine is malfunctioning. We reject the null hypothesis, but it was fine. The machine was fine, and we have stopped it for nothing. That is called a false positive, and more technically a type 1 error. The other possibility is a false negative. So it is a negative because we fail to reject the null hypothesis. So we cannot show that the machine is malfunctioning, and then we don't stop it because we don't have enough evidence to show that the machine is malfunctioning. But the machine was really malfunctioning, and that is a false negative. So the null hypothesis is false. That means truly the machine is malfunctioning, but we fail to reject the null hypothesis, so we don't stop it. So that is a false negative, or more technically, a type 2 error. Okay, so to understand how the hypothesis testing process goes, we need to understand how the data is collected, how the data is generated, and how this is translated into some calculations that we understand. Okay, so let's say that this is the distribution of the tablets, how they are manufactured. So remind, they have a mean of 250 and a standard deviation of 1. So the Gaussian typically goes from -3 sigma to +3 sigma. So we should see tablets typically between 247 and 253. And most of the tablets, or the most likely event, is close to 250. We chose one tablet, and this particular tablet has a weight or a compound, an amount of compound of 250.5. Okay, so let's call that amount x1. So x1, it is the first tablet. So what is the expected value of a single tablet, of that first tablet? Okay, so we have seen 250.5, but if I repeat the experiment, next time maybe I see 250, or I see 248, or I see 251. So what is the expected value of that first tablet? And the expected value of a single tablet, if the machine is working correctly, should be mu. It should be 250. And how much variance do I have in those amounts? I have the same variance as the manufacturing process. So if the the manufacturing goes from 247 to 253 in a Gaussian way, having a variance sigma squared, the variance of a single tablet is also sigma squared. That is actually the manufacturing process. Okay, so now, so this is a priori. A priori, this is what we expect. Okay, what about a posteriori? So a posteriori, I have collected one tablet. The weight or the amount of this tablet was 250.5. So if I have to tell what is my current estimate of what is the mean of the population, based on evidence, I have only one piece of evidence, that is this particular tablet. So I have to say that it is 250.5. I cannot say anything else. I don't have any more evidence. But okay, because we understand, if I repeat this process many times, the next time I repeat, the next week when I collect other 20 tablets, the first tablet will not be 250.5, it will be something different. So in general, it will be x1. So what is the expected value of my estimate of the mean? So this hat here means estimate. So this is the sample mean, this is the population mean. Okay, so the expected value, because my sample mean is equal to x1, the expected value of the sample mean will be the expected value of x1. So if the machine is working properly, should be also mu, and the variance, because these two variables are equal, the variance of my sample mean will also be equal to the variance of x1. So variance, when you are manufacturing tablets, it is how variable they are. When you are estimating a sample mean, what it means is how much uncertainty you have about that value. And I will have the same uncertainty as I have for my manufacturing process. Okay, so I have observed this one, 250.5, but I could have observed any one of these with these probabilities as shown in the graph. Okay, now I have my second tablet. So my second tablet now is 251.8. And then my sample mean is the average between the two tablets. So the mean between the first tablet and the second tablet, that is somewhere here in between. And the variance, so the expected value of these, you can make the calculations, but they are not difficult, but we will not do them here. So the expected value of these, if the machine is working properly, should be the 250. And the variance, the uncertainty that we have about that sample mean, now we have two pieces of information, two tablets. So we have a little bit less uncertainty. So how much less? Again, the calculations are not difficult, and we can show that it is sigma squared, that is the variability of the manufacturing process, but now divided by 2 because we have two tablets. So now this uncertainty that we have around the mean is a little bit narrower than what we had before. Okay, so now we add a third tablet. So the third tablet now it is 247 point something, and the average of the three is almost 250. So if I get an inspection now, I would be very happy because I'm almost on target. And again, the expected value of this sample mean is again the 250 if the machine is working properly, and the uncertainty that I have now about that mean is again a little bit smaller because we have three pieces of information instead of two. And then you keep adding more and more tablets. So you have 4, you have 5, and at some point you get to 20. So when you have 20 tablets, the mean that we have observed was 250.66. So this is centered around that value. Here we have all the tablets, and here what we have is the uncertainty. What we have in black is the uncertainty of our estimate about the mean. So with 20 tablets, we have quite a lot of evidence that 250, that is supposedly the target amount that we should have in each one of the tablets is a very unlikely value. So it is this deviation of 0.66, now it appears to be large in terms of what is the uncertainty that we have around our mean. So we have very little uncertainty, or little enough to show that the 250 is a very unlikely value. Okay, so let us try to formalize all that. So by the way, just a parenthesis in this digression. So we were talking before about descriptive statistics, making summaries. So, and we reported the sample mean. The sample mean was 250.66. But now, understanding how the what is the uncertainty that we have around that value, we can construct a confidence interval around that value. So it is what we have observed plus minus something, and this plus minus something is related to our uncertainty, and our uncertainty was sigma. In terms of standard deviation, it was sigma divided the square root of n, and also something that is coming from the fact that this uncertainty is attached to a Gaussian. So this set somehow accounts for the Gaussian, and the alpha is 1 minus alpha is the probability that the interval, this interval that we have constructed, really contains the population parameter. So in this particular case, our confidence interval with a confidence level of 5%, so that means 95%, with 95% probability, this confidence interval contains the population parameter. So we have observed 250.66, but the true parameter must be somewhere around here, and whenever you can, you should always report confidence intervals on your summary. So if you report a mean, a variance, a standard deviation, a correlation, or whatever, you should always give what is the confidence interval, how much uncertainty I have about that value. Okay, so now we come back to hypothesis testing. So we understand how the process is the process of the data generation and the data collection will be performed. And in this particular case, we have seen these values, these 20 values, but we understand that if I repeat the process, the experiment next week, I will get different 20 values. But the ideas about the expectations, the variances, the uncertainties, all those reasonings remain the same. Okay, so step one is understanding how the data is generated. And in our understanding now, a crucial point is that the data is Gaussianly distributed. Okay, so now, if the data is Gaussianly distributed and the null hypothesis is true, then we need to find a calculation that we know how it is distributed. And in this particular case, if the tablets follow a Gaussian with mean mu and variance sigma squared, then the expected value, the sample mean, will follow a Gaussian of centered at mu and with variance sigma squared divided by n. And then we can construct this calculation. This calculation is called the set. You may have heard about the set score. It is exactly this, or somehow related to this. And this set score, or this set variable, is a random variable. This random variable is take your sample mean, subtract the expected mean, so that is the 250, and then divide by sigma divided by square root of n. So in all setups, mu and sigma are fixed numbers. They are not random. What is random is your sample mean. So if you repeat this experiment every week, every week you will have a different sample mean. So that is where randomness comes in. And then this calculation will be distributed as a normal as a Gaussian with zero mean and standard deviation 1. So up to step 2, all we have done is to understand how the data is generated and think of a calculation that when we perform the experiment, we will know how it is distributed. Now, between steps 2 and 3, you perform your experiment, you collect your data, and you compute what is your sample mean. And in our case, it was 250.66 minus 250, that is the population mean, the expected population mean if the null hypothesis is true, divided by 1, that is sigma, divided by the square root of n. Okay, so in our case it is 2.97. So we have seen a deviation, a positive deviation of 0.66 milligrams. And this 0.66 milligrams with this uncertainty translates into a set value of 2.97. So we have to distinguish between this capital set, that is a random variable, and this small set, that is a sample from this random variable. Okay, so now the step 4 wonders, okay, how likely it is that if the null hypothesis is true, I get a set score or a set statistic that is at least as large as the one we have seen. So in our terms, we have seen a deviation of 0.66 milligrams. How likely it is that if the machine is working correctly, I see in 20 tablets a deviation of the sample mean that is 0.66 milligrams or more. And it can be, if it is more than 0.66, the set value will be larger than 2.97. That was our value. And it is as extreme to see a positive deviation of 0.66 as a negative deviation of 0.66. So we have to look on both sides. So either larger than 2.97 or smaller than minus 2.97. So you may have heard of these two tails tests. So this is the two tails. So if you don't know in which direction the deviation will occur, so the machine will deviate, you have to look what is the probability of having these deviations as large as this, but in both directions. Okay, so if you plot here the profile of the Gaussian 0,1, this is how it looks like, and then we look for the probability of set larger than 2.97, that is this area, or set smaller than minus 2.97, that is this area. And these two areas altogether, they make 0.003 or 0.3%. So that means that if we repeat this experiment of taking 20 tablets for 1,000 weeks, only in 3 of them we would see a deviation that is at least as large as 0.66 milligrams. Okay, so now the last step is to take a decision, and here is where the expert comes. The expert will set a threshold, and a typical threshold in biomedicine, it is 5%. So if your p-value, this calculation here is called the p-value. If your p-value is smaller than the threshold, then you reject the null hypothesis and you say that the alternative is true, or in our case that the machine is malfunctioning. Actually in biomedicine we typically put the stars on our results. So if the p-value is smaller than 5%, we put 1 star. If it is smaller than 1%, we put 2 stars. And if it is smaller than 0.1%, we put 3 stars. So our result here, it will take 2 stars. Okay, so now here is the expert of Sam Ewing. So now we would blame the hypothesis test for the responsibility of stopping the machine. So it is not our somehow decision, but it has been an automated decision. So hypothesis testing is actually a way of automating decision making. Okay, so what we have done is called a significance test. So in a significance test, we show that some parameter is different from a prescribed value, for instance. But it could be, you may remind that I said we either reject the null hypothesis or we don't reject it, we never accept it. So what you want to show is goes to the alternative hypothesis. So we want to show that the machine is malfunctioning to stop it, and then we put that hypothesis, the machine is malfunctioning, into the alternative. If we want to show that the machine is working correctly, we should put that into the alternative, and this seems to be a simple change, but it has a lot of implications in the calculation. So they all use the same kind of bricks, so confidence intervals, p-values, and these kind of things, but the way that they are combined, they are totally different. And we may want to show that our mean is larger than something, that or that it is larger or equal something. So whatever you want to show, you have to put it into the alternative. Okay, so now how knowing how you will analyze your data helps us to determine what is the sample size. Okay, so that is called power analysis, and sample size calculation by power analysis. Okay, so let's summarize again the analysis path. So you have defined a null hypothesis, and once you define the null hypothesis, the alternative is automatically defined because it has to be the opposite. So the opposite of being equal is being different. And then if the null hypothesis is true, you know that this calculation that we defined before is distributed as a normal 0, 1, and this difference in the numerator, it is the difference between the sample mean and the target mean. So that is the 0.66 milligrams that we have observed in our 20 tablets. Then we plugged in our data, and then we get this 2.97. Then we have calculated how likely it is that if the null hypothesis is true, we observe a value that is at least as extreme as this one, and it was 0.3%. And because this p-value was smaller than a threshold, we have rejected the null hypothesis. When you want to compute the sample size, how many tablets do I need to evaluate to be able to say that my machine is malfunctioning? You have to define a target. You have to define, what do I want to detect? I want to detect deviations as small as 0.5 milligrams, let's say, or 0.1 milligram, or you define what is your accuracy. This doesn't mean that the machine, that you are forcing the machine, or you are presuming that the machine will deviate this much. This means if the machine deviates this much, I want to see it. I want to be able to say that it is malfunctioning with a false positive rate that is below a given threshold, and our threshold is 5%. And you need to know how your manufacturing process varies. So you need to know the variability of your observations. That in tablets it is how much, what is the deviations for each one of the tablets. If you are working with animals and you're measuring the gene expression of a particular gene, you need to know what is the variability of this gene. And in the null hypothesis, that is, in the natural population of mice of this kind, what is the natural variation of the expression of this gene? And okay, so we know our process, the variability of our process, and then I know this column is when you perform the experiment. This column is before doing the experiment. So I know before you do the experiment, I know how you will process the data, and I know that you will reject the null hypothesis if the p-value is smaller than this 5%. This 5% is the confidence level, and it is the probability of these false positives. So it is the probability of rejecting the null hypothesis when it is true. So that is called alpha in the field, and this alpha is 5%. So I know that if your p-value is smaller than 5%, then you will reject the null hypothesis. Okay, and I know that you will do a two-tails test. So I can go back to this curve and look for a point such that the area from that point to the right and from minus that point to the left is exactly 5%, because I know that if your point, if your set statistic is beyond that value, beyond in this particular case for 5% it is 1.96. So I know that if your set statistic is larger than 1.96, you will reject your p-value will necessarily be smaller than 5%, and then you will reject the null hypothesis. So this 1.96 is a value such that the area on the right is 2.5%, the area on the left is 2.5%, and then in total we have this 5% of false positive rate. And I know that if your set is larger than 1.96, your p-value will be smaller than 5%, so you will reject. Okay, so I use that knowledge so that you can put the comparison at the level of p-value, or you can put it at the level of set. So I will put it at the level of set. So I copy the definition of set. So this is set, and set, if set is larger than 1.96, I know that you will reject the null hypothesis. Okay, so let's say that the deviation is as small as this 0.5 milligrams. So I know, because I have designed it, I want to detect 0.5. So in the case it is 0.5. This is delta, this is the deviation, this is called actually the effect size in the field. And so the effect size is 0.5, the variation of my observations is sigma, and then I know everything from this equation except n. N is the number of tablets I need to evaluate, and n, you solve for n and it turns out to be 15.4. So, and there is a condition here, it has to be larger than this, so you never round down, you have always to round up. Okay, so we would take 16 tablets to check whether my machine deviates 0.5 milligrams or not. So I don't know, before doing the experiment, I don't know if the machine will deviate or not. But what I know is that by following this procedure, if it deviates as little as 0.5 milligrams, with 16 tablets, I will be able to tell whether the machine has deviated or not, and I have limited the false positive rate to 5%. Okay, so let's see how it works. So here is the same formula, but now a little bit more formal. So this is the 1.96 that we know that on the right of that point we have 2.5%. That is why we have this alpha divided by 2. And then it will be the 1.96 times sigma divided by delta. Okay, so let's see how this formula works. So let's say that I want to be more confident. So not having a false positive rate of 5%, but I want to have a false positive rate of 1%, of 0.1%, because if I stop the machine without having to, my boss will kill me. Okay, so if I want to be more sure, alpha will be smaller, 1 minus alpha will be larger, and then if 1 minus alpha, you may notice that this area, so this area on the right would be alpha half, this area on the left would be alpha half, and the area in between is 1 minus alpha. So if 1 minus alpha is larger, the 1.96 critical limit, it moves outwards, so that we have a value that is larger than 1.96. So this set would be larger now. And set being larger means that the number of samples has to be larger too. So, and it makes sense. If you want to be more sure about stopping the machine, you have to collect more evidence that the machine is malfunctioning. And let's say that my tablets are more variable. So instead of having this standard deviation of 1, let's say it has a standard deviation of 2. So detecting half a milligram deviation when the tablets are more variable, it is more difficult. So if it is more difficult, I need more tablets. So what about if I want to be more sensitive? So instead of detecting 0.5 milligrams, I want to detect deviations of 0.1 milligram. So if you want to be more sensitive, very small deviations, you need to collect more data so that you are sure that this deviation that you have of 0.66 is really significant, and or 0.1 is really significant. So if the effect size is smaller, it goes into the denominator, and then n has to be larger. And there is a kind of technical effect here, but it makes sense too. So you probably have heard about one-sided tests or two-sided tests. So let's say that you have been working with this machine for the last 5 years, and you know that this machine, if it deviates, it always deviates in the direction of putting more. It has never deviated in the direction of putting less. So that is a priori knowledge. The more a priori knowledge that you put into your system, the fewer samples that you need to prove anything. So on the other side, if the machine sometimes deviates putting more amount, or sometimes deviates putting less amount, then you have more uncertainty, and more uncertainty requires more samples. So this difference between one tail or two tails translate into the 1.96. So the 1.96 was a point such that up to that point we had an area, a probability of 1 minus alpha half. If it is only one side, then instead of 1 minus alpha half, it would be 1 minus alpha. And then 1 minus alpha, the set of 1 minus alpha is a little bit smaller, not too much smaller, it is about 1.8. So it is a little bit smaller than 1.96. But it has an important consequence when you are working with animals. So if you are trying to prove that your vaccine, that your treatment or your vaccine is effective, you are only interested in proving on one direction. So one direction means your hypothesis, your alternative hypothesis, is using one of these two signs. You don't want to show that your treatment is different from not doing anything, but different in the sense that it may cure you or it may get you worse. If it gets you worse, it is not that I don't care, it is that I'm not interested in showing that my treatment really gets you worse. What I'm interested in is that it gets you better. And if it gets you better, I need to show only one side, and then I need a little bit fewer animals than if I don't know. I don't know in which direction my treatment will affect. I don't know, maybe the gene expression of this gene, I don't know if it will increase or it will decrease. Then I have to look into both sides, and I will need more animals for that. Okay, this is only part of the story, because where is the word power? It was called power analysis. What is power? Power is related to the false negative rate. Okay, and here it goes. Okay, so let's say that here we have in blue, we have the null hypothesis. So this is the uncertainty that we would have on the sample mean if the null hypothesis is true. So we should see values around 250, and now this sigma is sigma divided by square root of n, because what we are plotting is the Gaussian associated to the sample mean, not the Gaussian associated to the tablets. Okay, and let's say that the alternative is true. So the machine is really malfunctioning, and just for being consistent with our example, let's say that the machine is malfunctioning with a deviation of 0.66. It could be whatever, and actually when you design, it would be centered at 250.5. Okay, now let's say that the machine is really malfunctioning in this way, and this red line is we have mentioned that we can put the limit, the decision, on the p-value. We could put it on the set value, but I could also translate it into mu. So if the sample if the sample mean is beyond this point, I would reject the null hypothesis. Okay, and beyond this point, so I have seen 250.66. That is why I reject the null hypothesis, because it is beyond this critical value. And what is the probability that if the machine is malfunctioning in this way, I'm not able to reject the null hypothesis? I will not reject the null hypothesis if my mu, my sample mean, is before this critical value. So in all these places, I will not reject the null hypothesis. But actually what happens is that it may be that the machine is really malfunctioning, but because I have been unlucky with my tablet, I'm not able to show that the machine is malfunctioning because the sample mean is not beyond the critical value. What is the probability of that? It is all this area. All this area here in black is the probability that the machine is malfunctioning, but I'm not able to show it. And that area is called beta. That is the probability of a false negative result. And what I have to design is n such that this area, when this is centered at 0.5, 250.5, that is the half milligram that I want to use as the value for my detection. When it is centered around 250.5, this area in black is beta. It is you decide what beta is. So let's say it is 10% or 5% also. Okay, and then you have everything, and we will not enter into the equations here, but the equations here, you know everything except n. So you can solve for n in the same way as we did before, and now what we have is something that is almost the same as we had before. So we had before all these terms except the one on the false negative rate. So now the one on the false negative rate comes here. It is also related to the Gaussian distribution, and this beta, that is the false negative rate. And yeah, so and here in the denominator, what we have is the effect size. What do you want to detect? So now, if I want to detect 0.5 milligrams of deviation, I want to be sure that when I stop the machine, I should really stop it. And if this effect, this deviation happens, I want to be able to see it with this power. So this power means if the machine is malfunctioning, I really want to have a really low probability of not rejecting the null hypothesis. And if we think of this beta, we also want it to be relatively small. Let's say that you have a very large beta. You have a false negative rate of, let's say, 90%. So that means that 90% of the times that the machine is malfunctioning, you are not able to show that it is malfunctioning. So you would be a very bad engineer for that. And in terms of research, if 90% of the times that your treatment is effective, but you are not able to show that the treatment is effective, for that I don't do any research, because I stay at home and I'm much more comfortable. So beta, you want it to be low, maybe not as low as alpha. So when you say, I'm sure that this is working, you really want to be sure. When most of the times you know that your treatments will not make a difference, you don't want to be so precise in beta. So beta, typical values for beta, it is somewhere between 5 and 20%, but no larger than 20%. And we have made the reasoning based on positive deviations. We could do the same reasoning, but now on negative deviations, and the reasoning would be exactly the same, and the n in this particular case is exactly the same. So the formula for the n is the same for left and right deviations, and the reason is that this Gaussian in the middle for the null hypothesis is symmetric. So because the Gaussian is symmetric, then the formula for the n is the same. But in general, this is not the case. But this reasoning that we have done now on both sides, it is this power analysis. The power analysis is, okay, this is the distribution, this is the uncertainty that I would have on the sample mean if the null hypothesis is true. This is the uncertainty that I would have on the sample mean if the alternative is true, either because it deviates more or it deviates less. So then, so it puts more amount or it puts less amount. And then this power is 1 minus beta. So 1 minus beta is this area here. So that is why you have designed what is your sample size based on a power analysis. So based on looking for these critical values and then making that from the area under the null hypothesis, the blue one, under the null hypothesis, the area from the critical value to the right, it is 2.5. That is a two-sided hypothesis test. And then for the alternative, you have 1 minus beta on the right and 1 minus beta on the left. So yeah, and this is for two-sided statistical test. This is for a one-sided statistical test, but the formula you see, it is mostly the same. So if you want to have more power, you also need a larger n. This is what it is implied here. So the rest of the analysis is the same as the one we had done before, and now if you want to have more power, this set will be larger and you will need more samples. And it is important to note that the dependence of the sample size on all these parameters is quadratic. That means that if you want to change any one of them, the n will grow quadratically with the change of your sigma, the sensitivity, or whatever. So yeah, just to keep in mind, if I want to be very sensitive, so small effect sizes, I need a lot of samples. If my observations are very variable, I need more samples. If I want to have a lot of confidence in my rejection, and I want to be very sensitive so that I don't have many false negatives, you need more samples. So that is the take-home message. The exact calculation for all the other tests, they're different. They have the same principles, and this kind of plots, they appear all the time. So when you want to compute n, you have to do it through this power analysis, and you have to fix what do you want to detect. That doesn't mean that it will happen, but if it happens, you will be able to detect it with this confidence and this statistical power. There is a kind of rule of thumb of how many samples I need. This is called the resource equation, or MET's resource equation. In a simplified version, it has different flavors, and I don't want to get into the details, but somehow it is related to something called degrees of freedom that we will see a little bit in next session. And these degrees of freedom are here, and this is the number of degrees of freedom. So this is on the left you have the number of degrees of freedom that you get by doing your analysis. On the right you have the number of degrees of freedom that you spend in estimating different parameters. And so, for instance, let's say that you have a number of treatments. You are comparing 2 treatments to a control, so you would have in total 3 different groups. So T would be equal 3. Let's say that you are analyzing differences between males and females, so you would have a blocking variable that has 2 values. So B would be equal 2, or you are not using blocks, then B would be equal 0, and then you have a number of degrees of freedom for the residuals that for the moment we don't know what it is, but it is advised that the number of degrees of freedom for the residuals is somewhere between 10 and 20. Okay, so this resource equation, it is good to use. Let's put it differently. It is a very simple approach to a blind effect size choice. Okay, so here we have explicitly said I want to detect 0.5 milligrams of deviation. This resource equation somehow is also fixing that. So for instance, here we have different possibilities. I have given an example where we have beta equal 10%, so a false negative rate of 10%, a false positive rate of 5%. We are studying 3 groups that could be the control and 2 different treatments, and we are not analyzing differences between males and females. And so we have 3 groups, and we can put, let's say, 4, 6, 8 animals per group, and this is the total number of animals, and this is the number of degrees of freedom that the residuals would get. So we go from something close to 10 to something close to 20. We cannot get exactly 10 and 20 with the same number of animals in each one of the groups. And then the effect size, that again now it is much more difficult to define what the effect size is. Here you have the definition, but okay, let's not get into those details. But here the effect size would be, so if you use more animals, you can detect variations in the treatment that are in the order of 0.8 times the variations in the errors. And if you use fewer animals, instead of 0.8, you are a little bit less sensitive, 0.9, 1.2. So fixing the numbers of degrees of freedom for the residuals between 10 and 20 somehow is implicitly choosing what is the effect size for you. I think it is much more valuable to define yourself, what do I want to detect. You choose the effect size, and then you would use a power analysis to calculate how many animals you need. Actually, it is interesting that in all serious books about sample size calculation, the resource equation is not even mentioned. So so far for this session, and in the next session we will get a little bit deeper into statistical inference and this hypothesis testing that we have been doing. And that's all for now.